So to review the definition of a system of equations, remember a system of equations is where you have two or more equations. We've only been looking at situations in that previous investigation where we just have two equations, but you can have more, where the x and y variables in each equation represent the same thing. So remember, that doesn't mean that x and y mean the same thing as each other. It just means if you have two slope-intercept equations, in both equations, x refers to the same thing. So it could be a number of miles, it could be a number of weeks, it could be a number of movies, a number of hours, whatever your x variable is. And y on the two equations would mean the same thing. So it could be a total amount of money left. It could be a total amount of cost, like in the previous investigations. It could be a distance traveled, something like that. So they can go on the same graph, and an xy point on that graph means the same thing for both equations. So these problems are actually really common, where two things start at different values and change at different rates, but they share a point where the xy solution for one equation matches an xy solution for the other equation. That shows up on a graph as an intersection point of the two lines, or in a pair of tables, it would show up as the xy point in each table that is exactly the same. And then next year, you'll learn how to set up an algebraic way of solving these, which actually saves a lot of time and is much more precise than using a table or a graph to solve. So a couple examples of scenarios where systems of equations would help you solve a problem. Anything involving like saving or spending money. So you've got different savings plans or different spending patterns, and you're trying to figure out at what amount of time would the two patterns share the same value. A really good example is like cell phone plans, because cell phone plans tend to have options where it's just a flat rate, or maybe there's a flat rate plus an extra amount per gigabyte of data, or something like that. And so if you're trying to figure out maybe what two cell phone plans work best for you, you might be looking for the system of equations, like at what number of gigabytes of data usage would two different plans actually cost the same. So if you use a ton of data, it might make sense to pay a little bit more for the flat fee and less per gigabyte of data. If you don't use very much data, you might be better off with the plan that has the cheaper fee, but more expensive data past a certain point. So a lot of situations where these systems of equations would be used to solve. The classic math example of a car leaving Chicago and a car leaving Seattle and driving towards each other at different rates and trying to figure out at what point they would meet, that's a system of equations problem. Or if you have, this actually happened to me last winter, we were going with some friends over to Eastern Washington in separate cars, and we left at different times. So I had left a little bit later. My friend Carl had a head start. We were driving at different speeds, and knowing how far ahead of us they were, and knowing that Carl drives slowly, I was actually able to figure out how fast I would have to drive in order to meet up with them by the time we hit Wenatchee for lunch. So that's a system of equations type pattern. You're looking for the point where we had both driven the same amount of time, but we had gone the same distance. Or sorry, different amounts of time, but the same distance. So anyways, we're going to practice doing this. Instead of using scenarios, we're just going to practice using our skills of graphing slope-intercept equations to graph a system of equations. And then we're going to look at how you find the solution to the system and how you know that that's the correct solution to the system by doing some substituting and solving. And I'll show you how to use Desmos to check your work on these. So in example A, notice there's no scenario, but we just have two slope-intercept equations that we want to graph. And we're trying to figure out what is the xy pair that these two equations share. What is the solution to this system? And so we have found that the most effective way to estimate that is by graphing the two. And so what I'm going to do is just review graphing a slope-intercept line. This is from that last block of work that we did, reviewing slope-intercept equations and how to graph them. So we're going to graph each line and then find the intersection, and then we'll look at how we check to see if we found the correct intersection and graphed our lines the right way. So to graph 2x minus 5, I'm going to do this one in green. Remember, we want to start at the y-intercept. For this one would be at -5. So my y-intercept is down here at -5. So x is 0, y is -5. I got that right from the equation. And then my slope is 2. So remember, that means it goes up 2 over 1 from point to point. So then I'm going to go up 2 over 1 because that's my slope, 2 over 1. And it's positive, so it's going up to the right. And I'm going to do that a couple times. Up 2 over 1, another point, and another point. So that is coming right from my slope, up 2 over 1, and it forms a nice straight line. So remember that line, the solid green line, every single point on that green line is an xy pair that makes that equation true. So I don't have to calculate every single one. The line represents that set of solutions. So now I'll do the same thing with my second equation. So this one has a y-intercept at 10. There's my y-intercept at 0, 10. When x is 0, y is 10. Again, that's right off the equation. And then this one has a slope of -3 over 1. So remember, if your slope is a whole number, it means that that whole number is the rise, the up or down from point to point, and the run is just 1 if it's not written as a fraction. And this one has a negative slope, so that means I'm going to go down 3 over 1 from point to point. So down 3 over 1, that's another xy solution to that equation. Down 3 more over 1. So I'm going down 3 over 1 from point to point and establishing that pattern. Ooh, and notice if I go down 3 over 1 again, bam, I hit the other line. So there's my solution right there, the solution to the system of equations. Okay, so on this one, notice, looks like the solution to this system of equations is about x is 3, y is 1. And so we want to verify that that solution is correct. So when we verify that your solution is correct, that just means we're going to put 3, 1 into both equations and make sure that it makes both equations true. So for the first equation, y is 1 when x is 3. We're just seeing if that's correct. And it is, because that would be 6 minus 5, which is 1. So it works for that one. But I'm also going to make sure that I've done this correctly by putting that xy solution into my other. So y is 1, I have -3 times 3 plus 10. So -3 times 3 is -9, and -9 plus 10 is 1. So what this means is that I found the correct solution to the system of equations. If I had put in that xy point and it made one of the equations incorrect, so if 3, 1 wasn't actually one of the solutions to that equation, then that means that I either graphed my lines wrong and found the incorrect intersection point, or maybe I did my calculations wrong when I put that intersection point in. So you want to go back and check your work because there's an error somewhere. And a great way to check your work is using Desmos. Now remember, so you're going to be doing this exact process for the practice set down here. You're using Desmos as sort of a final check, or maybe to help you catch a mistake you had made in your graphing, to see which parts maybe you had done correct and which part had an error. If you end up getting something that doesn't work, like when you put your XY solution into both, and maybe it doesn't work for one of them, and you're trying to figure out where your mistake was, Desmos is a good place to check it. You're not using Desmos to do your work. And that's a really important part. You're not doing your work on here. So on Desmos, what this looks like is over here, you can just type in your slope-intercept equation using y and x. So I've got my y equals 2x minus 5 and y equals negative 3x plus 10. There's my red line and my blue line. And in Desmos, you can just click on those lines, click near the intersection point, and it will tell you the solution. So you can see that on this one, 3, 1 is the correct solution. The lines that Desmos graphed look like the lines that I graphed. So you can check to see if maybe if you have a mistake, maybe it was your graphing that was incorrect. Maybe you found the right place where the lines intersect, but one of your lines is in the wrong place. It doesn't represent the correct equation. And so it's not a solution to that system. It's a solution to some other system of equations. So it looks like I did this one right, and we're ready to move